So welcome to this class now, and in the last class we described some contrast, image contrast, and we described the intensity variation as a function of S and T. These two are the very important and also the importance of psi g, which is the extinction distance. Now we will see that how this contrast is used to analyze the defects in the samples. So I will just briefly get to the examples. Okay. So we have gone through those two equations, okay, where those two equations resembles related to your d phi 0 and dz, and the amplitude of the change in amplitude of diffraction with respect to the thickness, correct. So here the first term, as I told you, it corresponds to the scattering from the undeflected beam, which is related to your phi 0 in both the terms, okay, and the second term is corresponds to your phi g, scattering from the diffracted beam. Now if you assume there is a crystal which is having a certain defect, okay, if you have any crystal and if there is any defect or dislocation, so a crystal defect disturbs the operating planes. It means that locally, due to the presence of defect, the deviation parameters will change. What are the deviation parameter? Especially the S. Okay. This is due to the bending of the planes. This is related to your bending of the planes. Okay. And this particular, if there is a presence of defect in the crystal, then you will have an additional term which is related to your in the forward intensity, which is related to 2 pi g dot r. Okay. And this g dot r, g corresponds to your operating diffraction vector, or we can tell it as a reciprocal lattice vector. Okay. And r is the represents the displacement of atoms from their lattice positions due to the defect, and this displacement may actually vary along the z. Okay. So this is the r is the displacement vector. Now g dot r, okay, so here g dot r is the condition where the defect has on the operating planes. Okay. It means that if your g dot r is equals to 0, the displacement do not distribute the operating planes. So your what will happen is your defect will be invisible. So we use the invisibility criteria to identify the nature of defect. So how the nature of defect is identified? It is related to the Burgers vector, correct? It is related to the Burgers vector. Now Burgers vector, it depends upon your crystal system and the type of dislocation which is present in the sample. Okay. So you can use this g dot r criteria to identify when the defect will be visible and when the defect will be invisible. This criteria is very much understand to know the Burgers vector of any dislocation in the sample. Okay. So here there are two images where you can see that there are reflecting planes, correct, and your these are called your incident beam, these are reflecting plates, and you can see that the orientation in the first case, the orientation of the dislocation. So, this is your dislocation which is present on a certain other plane. This dislocation, the Burgess vector of dislocation is in this particular direction, correct. Now, you can see that this particular dislocation does not affect the incident beam, because it is carried on those particular reflecting planes. But in the case of second case, where you have the lattice planes, okay, these are the lattice planes, you can see that these are not on those planes, the defect is not present on those reflecting planes. So, these can diffract. Okay, so, this is how we can see the invisibility criteria for the defects. Now, I will give you 2 or 3 examples of dislocations and also the stacking faults. Fine. Now, in the first case, I will talk about the stacking faults, because stacking faults, grain boundaries, phase boundaries, these are all present in most of the microstructures. Okay. So, in the left side, you can see that the schematic of orientation of certain planes, okay, and these planes, these are cut by a stacking fault, and you can see that it imposes a plastic strain. Okay. In the first half, in the first part, this is your first part, this is your second part. In the first part, you can see that the R is equal to 0 for all positions above the fault plane, correct. But in the second part, R is not equal to 0, R has a certain value, the deviation has a certain value below the fault plane. Okay. So, while going across the stacking fault, your R changes. It means that fault has a displacement, but you can see that the S, the deviation parameter S is equals at the top also and is equal to the bottom also. So, you are assuming that your S does not vary. So, there is no bending in the sample. So, there is no change in S, but there is a change in the R. At the top R is equal to 0, at the bottom R equal to R. It might possible that the sample is bent and the fault has misorientation also, so that S also changes. It might possible that there is a bending along with your R changes. So, this also has a contribute towards the diffraction contrast. So, in certain circumstances, we call it as R as a displacement and your S contribution is called the misorientation. Okay. And it might possible that the contrast in imaging can be resultant of both R and S, can be resultant from the both R and S. So, based on the appearance, you can see that at certain locations, at each locations there is a change in the, while going, the intensity goes along the thickness, your R changes while moving across the stacking fault, and due to the interference between these beams, the beams that are diffracting in the upper part of the crystal, there is a difference between the beams the diffracting in the lower part of the fault. So, there will be a phase change at the fault plane. Okay. So, depending upon the vector which is used for the imaging purpose. If your G dot R is equals to 0, then the stacking fault contrast will be nullified or will be 0. Means it is, if G dot R equal to 0, then your stacking fault will appear as a single crystal, there is no contrast in the image. Okay. So, in this figure the R for this particular, this is 1 by 6 112, and you can see that in this third condition you can see that if the G is 2 bar 0, then your G dot R becomes 0, and you can see that the fault are not visible as these fringes in the third case. So, this is called invisibility criteria to identify the stacking faults in the sample. So, this I am talking about when you have a single grain with a stacking fault across the planes, correct. It is possible that you will have a grain boundary where you have a 2 grains, where your the deviation parameter S1 and S2 are totally different, your lattice spacing is different. So, there is a G1 and G2, correct. So, this corresponds to your grain or phase boundary. So, if there is a presence of grain boundary, what will happen? There is a change in the orientation of the grain while going across the grain boundary when you have incident beam. So, there will be a change in the orientation. So, diffraction conditions on both sides cannot be described in terms of the same G, your G value changes. So, because your interlaminar spacing of this grain and interlaminar spacing of this grain totally changes. Okay. So, one grain if you set up with a 2 beam with G and G1 and S1, another grain it might possible that they are not in the 2 beam condition, they might be in the some G2 S2 condition. Okay. So, the grain boundary contrast usually it is similar to the thickness fringe contrast, where the first grain, it might possible that the first grain contributes to the intensity with a, but the other grain will not contribute, due to which there will be a variation in the intensity while moving from one grain to the another grain. So, you can have a diffracted grain which is bright and the another grain will have a dark. So, here there is an image of a presence of grain boundary, you can see these fringes which looks like a thickness fringes. This is due to the tilt or the grain boundary which is present in the differentiating the two oriented grains. Okay. Now, in this case it is a very simple example of line defects. Imagine this is the planes, these are the planes, crystallographic planes, and you can see there is an incident beam and there is a presence of a dislocation, and due to the presence of dislocation you can see that these are the bending of planes near to the dislocation. Okay, so there is a bending of planes. So, at the core of the lattice, at the core of the dislocation, the lattice is bent severely, okay, and the extent of bent decreases as we move away. Okay. So, if your crystals are in a 2 beam condition, if you orient your crystals in 2 beam condition, near to 2 beam condition, but not in Bragg condition, not in Bragg condition, then it might possible that the incident beam, due to the bent nature of the planes near to the dislocation, they gets Bragg affected. Bent planes, they gets Bragg diffracted, or it might this means that these planes are in the S equal to 0 condition where there is a Bragg diffraction. It might possible that the planes away from the dislocation, those are not exact Bragg's condition, or S is very large. So, you will see a contrast difference in the imaging by the dark lines you can see in this image. It means that at those locations the planes are bent, even though your particular grain is not in the Bragg's condition, but due to the bent nature it turns out that your S becomes 0 and there will be a diffraction. So, in the bright field you will see the dark lines, those indicates the presence of dislocation on the image. Okay. So, here the R, you do not have to remember this equation, but it is a function of your x, y and z for the dislocation, and the displacement field of a dislocation in infinite isotropic solid is given by this equation, where here mu is the Poisson's ratio, B is the Burgess vector and B is the edge dislocation. Similarly, for screw dislocation R is given by B phi by 2 pi. Okay. So, this is how we can identify what type of dislocation is present, and usually what we do is, if you tilt your sample, you orient your crystal in such a way that at different G1, G2 and G3 and G4 conditions you can take the image from the same region where the dislocation is present, correct, and based on the vector analysis G dot B, actually you can get the invisibility criteria where you can identify what type of Burgess vector is present for that particular dislocation. Okay. So, this is how we can identify the nature of dislocation in any sample. Here very nice schematic view from Professor Hovey's book, where you can see that there is a presence of dislocation. This is your bent planes, and you can see that away from the dislocation S is greater than 0, and down your S is your S is greater than 0, means it is in both these locations your planes are away from the exact Bragg's condition, which is S equal to 0. But due to the bent nature of this dislocation, you can see that S is equal to 0 at those bending regions. So, what will happen? You will see a change in contrast in the diffracted intensity. Fine. So, this can be used to identify the conditions where these dislocations will be invisible or not. Assuming that this is your bent plane, okay, and this is your dislocation present, and your Burgess vector is in the right direction. Assume that the delta k points into the plane of the paper in this direction, means your G vector is into the plane. Fine. Now, if you see the front view, your G vector is into the plane, G vector is into the plane. So, your G dot B is equals to 0. It means in this case your dislocation will not be visible. But in this condition, if you see in this particular condition, your G vector is into the plane, So, your G dot B is not equal to 0. So, you will see the contrast. Based on this contrast, here it is shown schematically that if you have a 4 dislocations in this in the orientation 1 and in the orientation of 2, if you take a bright field from a transmitted spot, you will see that all the 4 dislocations are visible, correct. If you do a 2 beam bright field image or the dark field image from this particular spot, which is having a G vector in this direction, correct. So, the Burgess vector for this particular dislocation in this direction, it is in this direction. So, you can see that the G dot B for this particular dislocations is 0. So, you will see that these are invisible in this condition. If your Burgess vector is, if your G vector is in this particular direction, you will see that these 2 dislocations are invisible in this condition. So, based on that, you can actually by using the invisibility criteria, you can solve which Burgess vector is corresponds to what type of dislocation in any sample. Okay. So, this is just briefly I have gone through your defect analysis in the by using the diffraction analysis, which corresponds to G and B vector. Here there is another nice example. Okay. So, you can see that this is in zone of 110 and these are the dislocation network. This is a dislocation network which are formed in a superalloy, which is FCC, correct. Now, you can see that the dislocation segments are divided into these 4 segments, which is having a Burgess vector at different directions, fine. And based on the G condition, like this image is taken in 002 bar where all the dislocations are visible, the dislocations which are taken in 1 bar and 1 bar 1 3, you can see that in this condition these dislocations are invisible, most of the dislocation, and in this condition the other dislocations are invisible. Okay. Now, we will just go through your another contrast, which is, as I told you, about the phase contrast. We have described the mass thickness contrast, we have shown the diffraction contrast, which is used for the imaging purpose, dark field bright field imaging, and also how to do the defect analysis in the sample. Now, we will come to the phase contrast. As I told you in the last class, that phase contrast is nothing but when an incident beam falls on the sample, the outward beams, transmitted and diffracted beam, are again merged to form a image, which is called a phase contrast image. It is the constructive destructive interference of those beams, okay. And this gives you a, usually this gives a structure at a very local scale in the Armstrong level, okay. So, here in the right side, in the bottom image, you can see there is a nanoparticle, and if you zoom this particular region, you can see a bright intensity spots, which is almost in the uniform, okay. And these intensities are nothing but the resultant phase or resultant phase of or intensity of the total transmitted and the diffracted beams. So, that resultant into a series of bright spots on the image, and these are nothing but your atomic structure of the sample from the region, okay. Now, if you go to a 2 beam condition, for example, you can see this is your central spot 0 spot, and this is your 1 bar 1 spot, correct. Now, if it is in a 2 beam condition, means you are allowing only one set of particular planes for the diffraction. What it means, there will be interference of only the central spot and this particular diffracted beam, due to which you will see the intensities corresponds to only 1 bar 1 bar 1 particular plane. So, that is why you will see these lines, and these lines are nothing but the atomic planes. You can see that if your G vector is in this direction, as I told you during in few classes before, your trace of that particular plane is corresponds to perpendicular to this particular G vector in the real space. Okay. So, these lines are corresponds to the 1 bar 1 1 planes in the sample. And if you are taking this phase contrast image in a zone axis, where you are getting a uniform intensities of the diffracted spots, then what will happen, the intensities of these all spots will have a resultant on these bright regions. This is it means that this particular crystal is in the zone axis, and this is nothing but the atomic structure along that particular 110 direction. Fine. Based on the 2 beam and based on the conditions, and if for example, it is possible that you have a sample, there is a precipitate inside your sample which is having a different d spacing or orientation, and your matrix has a different d spacing. Okay. If you go for a high resolution imaging, when an electron beam falls, the diffraction from your matrix and the diffraction from the precipitate, they will generate the diffraction intensities at different G values or at different G values. And if you take a profile, if you take a image at this particular condition, G1 condition, so that you are making a diffraction spot only from the matrix, you will get these lines which are the planes which corresponds to the matrix. If you take the precipitate spot x for the imaging, then you will see that the precipitate has a different lattice spacing, but these are parallel, both the spots, correct. Similarly, if you put the if you put the objective aperture on both the spots, the D which is a matrix, the X which is a precipitate, then what you get is you will get the overall intensity summing of these two intensities of these planes. So, you will get a this type of pattern, okay, and these are nothing but your Moire fringes, and actually you can deconvolute these intensities to resolve the actual d spacing of that precipitate and the matrix. Similarly, with the different G1, G2 and G3 values, and depending upon the aperture size, what type of beams you can select, you can get a different types of Moire fringes. Okay, you can see these particular Moire fringes. So, you will get different intensities which corresponds to a summation of these intensities of these two diffraction patterns. So, this is called a phase contrast imaging in the electron microscope. In an electron microscope, as a last few classes I have gone through some basics to understand, to just to give a feel that in a transmission mode what type of contrast you are getting it, what type of analysis we can do. We have discussed about the diffraction analysis, we have discussed about the diffraction contrast, images, and also the stacking faults. So, with these have a several applications. So, you will have a nature of stacking faults, vacancies, interstitials. You can actually antiphase boundaries. They have a different stacking fault. They have different planes and the Burgess vectors. Low angle, high angle boundaries, twin boundaries, coherent interfaces, strain fields, and precipitates and orientation can be investigated by electron microscope. Now, whatever analysis what we are doing up to here, it is related to the structure. As you go with my first class, where I told about the use of electron microscopy for the structural analysis, correct. These all analysis can be correlatively will be used with the atom probe. Okay. So, I will end this class now, and in the next class what I will do is I will briefly talk about what are the advantage of atom probe over electron microscopes while using the for the chemical information. Okay. So, we can get the chemical information in TM by using the energy dispersive spectroscopy, but however what are the advantages of atom probe, that I will cover it in the next classes. Okay. Thank you.